So in this section, it's about linear approximation of a function at a point. And what the idea is that if we're near a specific point, like the tangent line, the point where the line hits the curve, then points near that will be close to the actual value. There'll be some bit of being off, but we can approximate it by creating the equation of a line. And so I just want to remind you here, I'll do a little progression here. Y minus y1 equals m times x minus x1. That's the point slope formula. And from that, if we move the y1 over, and it starts to look like the formula they have here, where the y1 is your f of a, your m is your f prime of a, that's your slope, and your x1 is a. We get this equation of the line. And what I really wanted to get at is then to relate it to the formula that they're coming up with here. So I want to also illustrate from these graphs. See the orange curve and then the blue line is the approximation. If we're close to that blue line, or to that point of tangency, then the values are really close. They may not be exact, but they're close. And so sometimes close is good enough. So the approximation then, f of x value, is approximated by the f of a plus f prime of a times x minus a for x near a. And this is what I want to stress. And so if we have some value, we can use this formula where a is the value of the tangent line, the point of the tangent line. And then this will talk about the difference here between the value of x and that value of a. Tangent, line, point, and wanted value. Okay, so let's come on down here. And our general formula is L of x, it's linear approximation of x, is that f of a, that's like our y1, plus f prime of a, that's our m, times x minus a, where a is like the x1 value. Okay, so we have that. Now let's see how we can use it. So we have a problem like this. F of x equals the square root of x. Find that at x equals 9, and use the approximation to estimate the square root of 9.1. So first of all, we can say f of x equals the square root of x, as they said, but I'm going to call it x to the 1/2. Why? Because then we need to take the derivative of that. F prime of x is going to be 1/2 x to the negative 1/2, which is 1 over 2 times the square root of x. So given that we want square root of 9.1, our L of x, what we're saying is like L of 9.1. That's going to be approximately the square root of 9, the value that we can find easily, plus 1 over 2 times the square root of 9, so that's plugging that in, that's for the slope part, times, and the next part is the difference between the value we want, the 9.1, and the value we can easily find, the 9. So this is going to be 3 plus, and square root of 9 is 3, so it's going to be 1 over 2 times 3, which is 1 over 6 times 0.1, and that value is 3.0167. And if I use my handy dandy calculator to find the square root of 9.1, I get 3.01662. So it's pretty darn close there. Okay, fun stuff. Let's do another problem. Now we're going to do the cube root of x. So again, I'm sort of doing the cube root of 8.1. So we have, if f of x is the cube root of x, which is x to the 1/3 power, f prime of x is 1/3 x to the negative 2/3, or 1/3 to the 2/3. So let's put in our formula. So our cube root of 8.1 would be approximated by that cube root of 8, which we can easily find, plus 1/3 times 8 to the 2/3 times 8.1 minus 8. Okay. So what we have is 2 plus 1/3 times, and the cube root of 8 is 2, 2 squared is 4, 3 times 4 times 0.1. So it's going to be 2.0083. Okay. And that's it. A little complicated, but once you get the hang of it, it's not so bad. Let's try another one. We got linear approximation of a sine here. So find the linear approximation of f of x equals sine of x at x equals pi over 3 and use it to approximate sine of 62. So I did this kind of in 2 steps. Just recall that pi over 3 radians is equal to 60 degrees. And then we'll do the conversion. And remember, our conversion to go from degrees to radians is you multiply degrees times pi over 180. And that's where you get radians. Okay. So for this one, same type of thing. Our f of x is sine of x. So our f prime of x is cosine of x. So our sine of 62 degrees is going to be approximately sine of 60 degrees. It's something we can easily find, or we have all memorized, I'm sure, plus cosine of the 60 degrees. This is the derivative. And then times 62 degrees minus 60 degrees. And that would put it in degrees, but it needs to be in radians in the end. I mean, doing the sine and cosine of the 60 is the same as doing sine and cosine of pi over 3. And then we'd have multiplied by pi over 180. So I'll be honest, I'm not thrilled that they mixed degrees and radians here, but that's what they did. So what do we have? We have the square root of 3 over 2 times 1/2 times 2 degrees times pi over 180 degrees. And from that, I get 0.88 3479. Okay. See, my calculator's in radian mode, so sine of 62. No, it's in radian mode. Should be in degree mode. Mode. So sine of 62 is 0.882947.5. So it's really close for what we're doing. Okay, that's how linear approximations work. Let's do a few more. So now we're going to find the linear approximation for f of x equals cosine of x. So again, our f of x is a cosine of x, which means our f prime of x is negative sine x. And in this case, we don't have a specific value. We just want the formula that we could plug things in if we're near pi over 2. So our cosine of x will be approximated by cosine of pi over 2 plus negative sine, that's x up there, of pi over 2 times x minus pi over 2. So whatever x value you were trying to approximate, you plug it in there. Okay, so we have cosine of pi over 2, we all know that is 0, minus, it's plus negative, so minus 1 times x minus pi over 2. So it's interesting. This just comes down to be a negative x plus pi over 2. Or cosine of x is approximated by pi over 2 minus x. And by the way, I haven't said I'm doing those wavy equals, which means approximation. Okay, let's do another one. Find the linear approximation of f of x equals 1 plus x to the n at x equals 0. Use this approximation to estimate 1.01. So I want to stress here, this one, I was working through it a couple of times, and just that this x must be 0.01 because we're talking about 1.01 and 1 plus x. So again, our f of x is 1 plus x to the n power. So our f prime of x is n times 1 plus x to the n minus 1 times the derivative of what's inside is just a 1. So what we're just looking at there is n times 1 plus x to the n minus 1. Okay. So in this case, our x is going to be, let's see here. X is 0. Well, for the approximation, it's 0.01, but let's go through this. So our f of x would be approximated by (1 plus 0 to the n power). So this is the original function, and it's near 0. 0.01 is near 0. That's why I put in a 0 there. That's the part that kind of threw me off on this. Plus n times 1 plus 0 to the n minus 1 power times our 0.01. So this approximation would be 1 plus n times 0.01, and then the n in this case, it was the third power. So it's approximately 1 plus 3 times 0.01, or 1.03. So what we're saying is 1.01 to the third power is approximately 1.03. And let me see what I get on my handy-dandy calculator. 1.01 to the third power, 1.030301. Okay, we've got a couple more here. So now we're doing the linear approximation of f of x equals 1 plus x to the fourth at x equals 0. So what we just did. So our f of x equals 1 plus x to the fourth power. So our L of x, the linear approximation, is based on what we just saw up above. But instead of having the 0.01, and we'd have an nx, and instead of having the 3, we'd have a 4 because the power is 4. So that's going to be 1 plus n times the x that we haven't defined. So it's going to be 1 plus 4 times the x. That would be the linear approximation as a function, not as a value. So I'm just using what was up from there. Okay, moving on. And this one didn't print as well. So it says use linear approximations to solve the cube root of 125.4. So in this, our f of x equals the cube root of x, which is x to the 1/3. We've already seen one of these. F prime of x would be 1/3 x to the negative 2/3, which is 1/3 times x to the 2/3. Okay. So our linear function, L of x, is going to be defined by f of 125 plus f prime of 125 times our 125.4 minus 125. Maybe I should change this instead of L of x, L of 125.4. Okay, so that's going to be the cube root of 125 plus 1/3 times 125 to the 2/3 times 0.4. So that's going to be 5 plus 1/3 times 25, because the cube root of 125 is 5. 5 squared is 25 times 0.4. And we're going to get from that 5.00533. And let's see. Let me just look at the 125.4 to the power of 1 divided by 3. 5.005327. Wow, that's close for a ways. Okay, because that rounds up to 533. Okay, let's go on to, I think it's our last problem now. Also did not print out. Let's use this space here. So we have y equals 5x squared plus 4x plus 4. And this one they're asking for a differential. So, the book didn't really go into the differentials too much here, but the differential would be, it's what we call dy equals f prime of x dx. And so dx would be the change of the x. So what I'm trying to say, the dy is the little tiny change that occurred on the y part related to the change of the x part. And so what we're looking at is they give us a couple things. They want when x equals 4, and they want a dx of 0.2 and a dx of 0.4. Okay, so our y prime is going to be 10x plus 4. So f prime of 4 is going to be 10 times 4 plus 4, which is 44. So we have two things. We have the dx being 0.2. In that case, the dy would be 44 times 0.2, or 8.8. And then we have the dx being 0.4. In that case, our dy is 44 times 0.4, which would give us 17.6. Okay, and that does it for this section.